Hi everyone, have you ever seen a robot play the 古筝? Let's sing it. Looks amazing, right? But here's the secret. To make it play, the robot first needs to read the music score. That's exactly what we solved using deep learning. Let's get into it. Though the goal is to give the system a score image, and it outputs every note, what pitch, what type, how long, fully automatically. The trouble is that these symbols are tiny, super dense, and many looks almost the same. Move a dot one line up, totally different note. Rule-based methods just fail here. Deep learning, though, handles this naturally. We needed a false detector that works well with small dense objects. Enter ULV5. You only look once. That's the philosophy. One pass over the whole image and you get all the boxes and labels at the same time. No complex pipeline. It's also lightweight, so later it can run right on the robot. Its grid-based design is honestly perfect for dance-shaped music. Let me show you how. ULV5 divides the image into an S by S grid, like a chessboard on top of the score. Each grid cell is responsible for detecting any symbol whose center falls inside it. If a note center lands in your cell, you have to predict a bounding box around it, plus its class, quarter note, flat, whatever. And all of this happens in one shot. No second chance, no looking back. Just one clean output. But just saying there's a note somewhere in this cell is enough. We need exact location. That's bounding box regression. ULV5 adjusts the box center, weight, and height to keep the center from jumping around too much during training. We apply a sigma function. It clumps the offset to a smooth range. Really simple trick, but it makes a huge difference for those tiny symbols. When we train the model, we have to tell it how long its predictions are. That's the loss function. We choose CLOU loss. It cares about three things at once: overlap area, distance between box centers, and aspect ratio. This pushes the predicted box to hold the real symbol as tightly as possible. For small notes that are easy to miss, this precision is everything. Now, my teammate will take you through the experiment and conclusion.
Welcome to part 3 of our presentation. It's experiment. We have 4 parts on this. The first is a dataset preparation. This is a larger scale public music score dataset. It have a multiple difficult levels from beginner to advanced and high quality ground truth with a bounding both plus class labels. Also, it's a diverse symbol. It have a note, rate, clef, accidental, and dynamic. And last, we have 3 parts. The first is code implementation. Our algorithm implementation code is like this. The first is deep score virtual data normalization algorithm, and second is a music note and staff coordinate algorithm. S3 is important. It will determine which step each node in a score belongs to. The input is node and the staff coordinate, and output the staff to which each node belongs. And the length is our model comparisons. It comparison for key metric during model training and validation. This records the fluctuation in key metric of the object detection model during the training and validation process. The key observation is all those coverage modes indicate stable training. And second is random model show faster converges, high MAP. And the 3 is a validation metric training close and is no overfitting. And at last is a result demonstration. The final result of music score recognition. The simple example is visual ode to Joe. It's a good performance. And the complaints sheet music is digital blue and white precedent. Its recognition performance remained quite reliable.
So let's make a conclusion. This research addresses a crucial challenge in preserving intangible cultural heritage. the lack of efficient tools for digitizing traditional music notations. Our project follows this comprehensive research pipeline, moving from data collection to final conclusions and future directions. And as for the data processing, a key innovation was incorporating mosaic data augmentation, which significantly enhances the model's ability to learn from complex musical layouts by training on composite images containing multiple score fragments. So let's go to the results. The training progression reveals excellent learning dynamics. Both training and validation losses show smooth convergence with minimal divergence, indicating strong generalization capability without overfitting. Evidence of a robust training process. And our comparative analysis yielded decisive results. The YOLO V5X model achieved a remarkable MAP 0.5 exceeding zero point 0.9, substantially outperforming the YOLO V5M baseline. This performance gap demonstrates the larger model's superior capability in handling complex musical symbol recognition tasks. So, this work successfully establishes an effective pipeline for traditional music digitization, demonstrating that deep learning can significantly contribute to cultural heritage preservation through automated score recognition technology. Looking ahead, we plan to score transformer architectures for better contextual understanding and develop sophisticated symbol to performance mapping models to enhance the system's musical expression capabilities. That's all. Thank you.